Okay, in this second part of the webinar, we will discuss the industrial heat demand and best technologies to supply it at different temperatures, comparison of technologies for industrial heat demand, the Exceed grant, the air handling units for business and heat recovery and upgrade grant. We will discuss solar PV power, some notes on alternatives or complementary technologies for solar PV, notes on PV system design, and the Non-Domestic Microgen Grant. Industrial heat demand is strongly linked to temperature level because the available technologies and their efficiencies change significantly as temperature increases. Lower temperature heat is easier to supply efficiently using heat pumps and recovered waste heat, while higher temperature applications increasingly rely on direct combustion, electric resistance, or specialized high temperature heat pumps with lower coefficient of performance. A practical way to understand technology selection is to match the temperature quality of it with the most efficient available supply option. In this table, we assess industrial heat demand across different temperature levels, their typical applications, the most suitable technology options, and their expected performance. Very low temperature heat is in the range of 20 to 45 Celsius degrees, is typically used for space heating in well-insulated buildings, underfloor heating systems, ventilation preheating, and low-grade process needs such wash water preheating or mild drying. This temperature band is highly compatible with waste heat recovery sources such as refrigeration condenser loops, data center cooling systems, or ambient air and water sources. The best technology options are air source, water source, and ground source heat pumps, as well as heat recovery systems from chillers and/or industrial processes. These systems can achieve very high efficiencies, often with the COP values in the range of 2.5 to 6, depending on source condition and seasonal performance. This makes it one of the most energy efficient temperature ranges to supply. Low to medium industrial heat in the range of 45 to 90 Celsius degrees is commonly used for domestic hot water, space heating systems with radiators, cleaning and sterilization processes, food and beverage processing, pasteurization preheating, and low pressure washing systems. This range is still highly suitable for modern heat pump technology, particularly high-efficiency industrial heat pumps and upgraded waste heat recovery systems. Conventional heat pumps can typically deliver temperatures up to 60 70 Celsius degrees very efficiently, while newer high-temperature heat pumps can reliably reach 80 to 90 Celsius degrees with COP values typically between 2.5 and 4, depending on lift conditions. This temperature band is also where integration with refrigeration, heat recovery, and process waste heat becomes particularly effective, as many industrial systems naturally reject heat within this range. Medium to high industrial heat in the range of 90 to 150 Celsius degrees is used in more energy-intensive processes such as sterilizations, evaporation, drying, chemical processing, and certain food manufacturing operations. At this level, technology options become more limited, but high-temperature heat pumps are increasingly important. These systems, often using advanced refrigerants or multi-stage compression, can deliver heat up to around 120, 140 Celsius degrees, though with lower COP values, typically in the range of 1.8 to 2.5, depending on the temperature lift and design. Where heat pumps are not feasible, electric boilers, biomass boilers, biogas CHP, or boilers are commonly used. Waste heat recovery can still play a role, but if it often requires temperature upgrading via heat pumps or cascaded systems to become usable at this level. High temperature heat in the range of 150 to 300 Celsius degrees is typically required for heavy industrial processes such as steam generation for industrial processes, chemical production, distillation, high temperature drying, and certain manufacturing applications. At these temperatures, direct combustion remains the dominant technology, including natural gas, biomass, or biogas boilers. Electric resistance heating can also be used where low carbon electricity is available and grid capacity allows. As temperature requirements increase, the efficiency advantage shifts away from heat pumps and toward combustion or specialized high temperature systems. The most cost-effective and energy efficient strategy in industrial decarbonization is therefore to reduce required process temperatures where possible, recover waste heat to cover low temperature demands, and reserve high-grade energy sources for only the highest temperature requirements. High-temperature heat pumps, biomass boilers, and biogas boilers or CHP systems are all viable options for supplying industrial heat demand, but they differ significantly in temperature capability, efficiency, operating characteristics, costs, and policy fit. High temperature heat pumps can typically deliver heat in the range of about 90 to 160 Celsius degrees, depending on design and refrigerant system. Although performance declines as temperature lift increases, their efficiency is expressed as COP, usually ranging from about 128 to 4.0, with higher values achievable when there is a strong and stable low-grade heat source, such as waste heat from refrigeration or process cooling. They are best suited to steady base load heat demand and perform particularly well where there is a simultaneous cooling and heating, but they are less flexible for highly variable or peak-only loads. They generally have high capital expenditure due to complex technology and integration requirements, but lower operating costs, and typically payback periods range from about 4 to 10 plus years, depending on energy prices and system integration. CO2 abatement costs are often moderate, typically around 50 to 150 per ton, though can be lower where waste heat is available or electricity is low carbon. Operational complexity is moderate to high due to control requirements and integration with existing systems, and policy support is generally strong as part of electrification and decarbonization strategies. Biomass boilers can deliver a wide range of heat, typically from about 80 Celsius degrees up to 300 Celsius degrees, depending on whether hot water or steam systems are used. Their efficiency is typically high in combustion terms, around 80 to 95%, but this is not directly comparable to COP-based system. They are best suited to stable continuous baseload heat demand, where fuel supply chains can be reliably managed. They have medium to high capital costs due to fuel handling, storage, emissions control, and boiler systems. Payback periods are typically in the range of 3 to 7 years, depending on fossil fuel displacement and biomass fuel costs. CO2 abatement costs are often low and can even be negative in some cases, typically ranging from about minus 20 euros to 8 euros per 80 euros per ton of CO2. However, operational complexity is high due to fuel logistics, ash handling, maintenance requirements, and air emissions compliance. Policy support remains strong, but is increasingly constrained by sustainability criteria, air quality limits, and biomass sourcing rules. Biogas boilers and CHP systems typically deliver heat in the range of about 80 to 200 Celsius degrees, with CHP systems also producing electricity alongside heat. Overall system efficiency for CHP can be very high, often 80 to 90% total energy utilization when both heat and power are effectively used, although electrical efficiency alone is typically around 30 to 45%. These systems are best suited to continuous heat demand where there is also a beneficial use or export route for electricity, making them particularly valuable in industrial sites with stable baseload demand and grid connection capacity. Capital expenditure is generally medium to high, with CHP systems at the higher end due to engine systems, gas cleaning, and green integration requirements. Payback periods are typically around 3 to 8 years, depending on gas cost, electricity value, and utilization rates. CO2 abatement costs vary widely, typically from around 0 to 120 per ton, depending on fuel sourcing and system configuration. Operational complexity is moderate for boiler and higher for CHP due to maintenance and operational balancing requirements. Policy support is generally strong but increasingly dependent on sustainability certification and life cycle emissions accounting. High-temperature heat pumps are the most efficient long-term electrified solution where suitable heat sources exist. Biomass remains a robust direct heat option for high-temperature and baseload applications, and biogas CHP offers a flexible combined heat and power solution where integrated energy use can be maximized. The Exceed Excellence in Energy Efficient Design grant scheme is an Irish support program designed to help large energy users deliver highly efficient, low-carbon industrial and building projects by embedding energy performance at the design stage and funding both feasibility and implementation. The objective of Exceed is to reduce energy consumption and carbon emissions by ensuring that energy efficiency is considered from the earliest stages of project design rather than being added later. It promotes an energy efficient design approach that challenges conventional design choices and optimizes entire systems, building processes, and utilities to minimize life cycle energy use and improve competitiveness. What is funded under the scheme includes both pre-investment and capital costs associated with energy efficiency and decarbonization projects. At feasibility stage, support is provided for technical studies, energy modeling, and engineering design, and expert facilitation required to develop an Exceed compliant project. At the implementation stage, the scheme provides capital grant funding for eligible investments such as high-efficiency equipment, process upgrades, heat pumps, biomass systems, solar PV, and associated installation and professional service costs. In addition, projects that follow the Exceed process can receive certification support, which can unlock additional grant incentives. A key benefit of the scheme includes significant financial support for large-scale energy projects up to around 3 million per project, depending on eligibility, reduced energy costs, improved carbon performance, and better technical project outcomes due to structural design optimization. It also reduces investment risks by validating energy savings through a formal measurement and verification process, and can improve access to corporate sustainability and compliance reporting frameworks. Eligibility is primarily targeted at large energy users, typically organizations consuming more than around 100,000 kilowatt-hour per year, although it is open to all sectors. Eligible projects generally involve new buildings, major refurbishments, repurposing of facilities, or significant upgrades to industrial processes and energy systems. Applicants must be able to demonstrate a clear energy saving potential, a defined project scope, and commitment to following the exceed design methodology. Projects are assessed based on energy and CO2 savings, value for money, technical quality, and adherence to the exceed process. Grant details vary depending on company size and project stage. For implementation, capital investment grant support is typically up to about 30% for large companies, 40% for medium companies, and up to 50% for small companies, subject to value for money limits and maximum funding caps. A portion of the grant, often around 10%, may be retained until exceed certification and verification of savings is completed. Additional funding is also available for the design and feasibility stage, often covering a significant portion of eligible consultancy and engineering costs. The application process is staged. It begins with an initial feasibility and design phase where organizations develop and exceed project plan, energy balance, and savings. Once feasibility is established, the stage 2 application is submitted for capital funding. Then the proposal is evaluated based on eligibility criteria such as project definition, integration of the exceed process, project schedule, cost justification, quantified energy savings. If approved, a letter of offer is issued allowing project implementation to begin. After construction and installation, the project is inspected and verified, and final grant payments are released following confirmation of performance and, where applicable, certification. Comparison of technologies for heat recovery. Heat recovery enables energy-intensive industries in Ireland to significantly reduce fuel consumption, lower operating costs, and cut carbon emissions by capturing otherwise waste process heat and reusing it efficiently within operations. In this table, different technologies for heat recovery are compared. Heat exchangers, including plate and shell and tube designs, are among the most widely used heat recovery technologies and are suitable across a broad temperature range from approximately 20 Celsius degrees to over 600 Celsius degrees, depending on the application and materials used. They are commonly found in manufacturing, food and beverage processing, pharmaceuticals, HVAC systems, energy generation, and data centers. Heat recovery efficiencies typically range from 30% to 80%. Their main advantage are their maturity, reliability, relatively low cost, and ease of integration into existing systems. However, their performance depends on maintaining an adequate temperature difference between streams, and fouling can reduce effectiveness over time. They are a fully mature technology and are supported in Ireland through SEI Business Energy Upgrades Scheme and exceed grants. The boiler economizers recover heat from boiler flue gases, typically operating in the temperature range of 120 Celsius degrees to over 400 Celsius degrees. They are widely used in steam generation systems across industrial facilities, hospitals, and commercial buildings. Economizers generally deliver fuel savings of between 5 to 15% by preheating boiler-feed water. They are attractive because they are relatively inexpensive, straightforward to retrofit, and often provide short payback periods. Their effectiveness is limited by flue gas temperatures and the potential for corrosion if temperatures fall too low. Economizers are a mature technology and are eligible for support under CI business energy efficiency programs. Condensing heat recovery systems recover both sensible and latent heat from exhaust gases, making them particularly effective when return water temperatures are below approximately 55 Celsius degrees. They are commonly applied in gas-fired heating systems, district heating networks, hotels, hospitals, and commercial buildings. These systems can achieve an additional 10% to 20% energy recovery compared to with conventional heat recovery approaches. Their main advantage is the ability to capture latent heat from water, vapor, and flue gases, significantly improving overall efficiency. Their effectiveness decreases where return temperatures are high and condensate handling systems are required. They are fully commercialized and supported through standard SCI energy efficiency grant programs. Heat recovery steam generators are designed for high temperature waste heat streams generally between 300 Celsius degrees and 600 Celsius degrees or higher. They are most commonly used in combined cycle power plants, combined heat and power facilities, and large industrial processes. They can recover between 50 to 80% of available waste heat, converting it into useful steam for power generation or industrial processes. Their primary strength is their ability to capture very large quantities of high-grade waste heat. However, they involve substantial capital investment and are generally only economical at larger scales. They are a mature technology and can receive support through Irish industrial energy efficiency and decarbonization programs such as Exceed. Regenerative heat exchangers, often referred to as thermal wheels, are widely used in ventilation and air handling systems operating at temperatures ranging from below freezing to approximately 200 Celsius degrees. A thermal wheel works by rotating a heat-absorbing matrix between the warm exhaust air stream and the cooler incoming air stream, transferring stored heat from the exhaust air to the fresh air supply. The heat-absorbing matrix is mounted as a large circular wheel and is slowly rotated by a small electric motor and drive system, typically at speed of around 55 to 20 revolutions per minute, so that section of the matrix alternately pass through the exhaust and supply air streams to transfer heat continuously. They are common in offices, hospitals, educational facilities, data centers, and industrial buildings. Heat recovery efficiencies typically range from 60 to 90%. Thermal wheels offer very high efficiency and compact installation requirements, making them particularly attractive for HVAC applications. Their main limitation is the possibility of some cross-contamination between exhaust and supply air streams, as well as the need for ongoing maintenance and moving components. They are fully mature technologies and are supported in Ireland through SCI grants for air handling unit upgrades and ventilation improvements. Run-around coil systems are generally used where supply and exhaust air streams are physically separated and cannot be connected through a conventional heat exchanger. Run-around coil systems recover heat by circulating a fluid, typically water or water glycol mixture, between a coil in the exhaust or air stream and a coil in the incoming air stream, transferring heat without mixing the air streams, and are typically used for temperatures ranging from about 0 Celsius degrees to 150 Celsius degrees and achieve heat recovery rates of approximately 40% to 65%. Their key advantage is the complete separation of air streams, eliminating cross-contamination risks. However, their efficiency is lower than thermal wheel systems, and they require pumps, pipework, and additional controls. They are mature technologies and are eligible for support under ventilation and energy efficiency upgrade schemes. Industrial heat pumps are increasingly important for decarbonization and waste heat recovery. They typically recover low-grade waste heat at temperatures between 20 and 100 Celsius degrees and upgrade it to useful process temperatures ranging from 60 to higher temperatures depending on the technology. They are commonly deployed in food processing, dairies, pharmaceuticals, chemicals, and district heating systems. Rather than measuring recovery efficiency directly, performance is usually expressed through a coefficient of performance, which commonly ranges from 2 to 6. Their main strengths are their ability to electrify industrial heat production, recover low temperature waste heat, and significantly reduce fossil fuel consumption. Their limitations include higher capital costs and reduced efficiency when large temperature lifts are required. Industrial heat pumps are a key technology within EU decarbonization frameworks and are increasingly supported through SCI business energy upgrades, exceed, and other enterprise sustainability initiatives. Organic Rankine cycles systems convert waste heat into electricity using an organic working fluid instead of water and steam. They are most effective for waste heat sources between approximately 80 and 300 Celsius degrees and are commonly found in cement, glass, biomass, and industrial manufacturing sectors. ORC systems typically convert 5 to 20% of available waste heat into electricity. Their main advantage is their ability to generate power from heat sources that are too cool for conventional steam turbine systems. Their principal limitation is relatively high capital cost, which means economic viability depends heavily on operating hours and electricity prices. ORC technology is commercially proven but remains less widespread than conventional heat recovery technologies. Support may be available through SEI programs. Thermoelectric generators produce electricity directly from temperature differences using semiconductor materials. They can operate across a wide temperature range, but are generally most effective where large temperature gradients exist, typically above 100 Celsius degrees. Applications include remote monitoring systems, niche industrial recovery projects, and automotive waste heat recovery. Conversion efficiency are usually below 10%, making them less attractive for large-scale energy recovery. Their strengths include having no moving parts, low maintenance requirements, and compact designs. However, their relatively low efficiency and high cost currently limit widespread deployment. They remain an emerging technology and are more likely to receive support through research development and innovation funding than through mainstream energy efficiency grant programs. The absorption chillers use waste heat to produce cooling rather than directly recovering heat from heating for heating purposes. They typically require heat sources between 80 Celsius degrees and 200 Celsius degrees or higher, and are widely used in hospitals, district cooling systems, industrial facilities, data centers, and large commercial buildings. Their coefficient of performance generally ranges from 0.6 to 1.3. Their principal advantage is the ability to convert waste heat into useful cooling, reducing electricity consumption associated with conventional chillers. Their limitations include lower efficiency compared with electric chillers and the need for a consistent heat source. Absorption chillers are a mature technology and can be supported through Irish energy efficiency and decarbonization schemes, where they form part of a broader waste heat recovery project. Across Europe, these technologies are supported by policy frameworks, including the Energy Efficiency Directive, the Energy Performance of Buildings Directive, the Industrial Emissions Directive, eco-design requirements, and broader decarbonization initiatives under the European Green Deal and Fit for 55 package. In Ireland, the primary funding mechanism for heat recovery projects are provided by SEI through the Business Energy Upgrades Scheme, the Exceed Grant Scheme, and the Support Scheme for Energy Audits. These programs can support feasibility assessments, detailed design work, and capital investment in heat recovery and energy efficiency projects across commercial and industrial sectors. Solar PV. Solar PV provides low-cost on-site renewable electricity, reduces exposure to volatile energy prices and carbon costs, improves ESG performance, and supports long-term industrial decarbonization with relatively fast deployment and low operating costs. It is interesting to compare alternative or complementary solutions to solar PV, highlighting their strengths and weaknesses. On-site wind turbines are typically used at industrial sites, farms, water treatment facilities, large commercial campuses, and public sector sites with sufficient land and favorable wind conditions. Their main strengths are the production of renewable electricity with no fuel costs or direct emissions, and the potential to reduce dependence on grid electricity. However, output is variable and dependent on wind availability, planning, and permitting requirements can be significant, and suitable sites are limited by wind resource space and proximity to neighboring properties. Battery energy storage systems are used to store electricity for later use and are commonly deployed alongside renewable generation in commercial and industrial facilities, data centers, and grid support applications. Their strengths include rapid response times, the ability to reduce peak electricity demand, improve energy resilience, support renewable integration, and provide backup power. Their limitations include relatively high capital costs, finite storage duration, degradation over time, and dependence on charging from either the grid or on-site generation. Gas-fired combined heat and power systems simultaneously generate electricity and useful heat from natural gas and are widely used in hospitals, hotels, and manufacturing facilities, universities, and district heating schemes. Their main advantage is high overall energy efficiency, often exceeding 80% due to the utilization of waste heat that would otherwise be lost. They can provide reliable baseload power and heat while reducing energy costs compared with separate generation. However, they remain dependent on fossil fuels, are exposed to gas price volatility, and may face increasing regulatory and carbon-related pressures as decarbonization policies strengthen. Biomass and biogas CHP systems operate similarly to gas CHP, but use renewable fuels such as wood chips, wood pellets, agricultural residues, anaerobic digestion biogas, or landfill gas. They are commonly used in food processing, agriculture, district heating networks, and industrial facilities with access to sustainable fuel supplies. Their strengths include the generation of renewable electricity and heat, lower life cycle carbon emissions, and the ability to provide dispatchable energy. Their weaknesses include higher operational complexity, fuel handling and storage requirements, local air quality considerations, and dependence on a reliable biomass or biogas supply chain. Renewable grid power purchase agreements allow organizations to procure electricity from renewable energy projects such as wind or solar farms through long-term contracts. They are widely used by large industrial facilities, technologies companies, data centers, and public sector organizations seeking to reduce emissions without developing on-site generation assets. Their strengths include access to large volumes of renewable electricity, long-term price certainty, and significant carbon reduction benefits. Their limitations are that they do not provide physical backup power during outages, typically require long-term contractual commitments, and are generally more suitable for organizations with substantial electricity demand. Hydrogen backup generation uses hydrogen-fueled engines or fuel cells to provide standby or emergency electricity supply and is increasingly being considered for data centers, critical infrastructure, and industrial facilities pursuing deep decarbonization. Its primary strengths are zero direct carbon emissions at the point of use when supplied with low-carbon hydrogen, long-duration energy storage potential, and compatibility with the future hydrogen infrastructure. However, hydrogen generation, storage, and distribution infrastructure remain underdeveloped in many regions. Equipment costs are high, and the overall economics depends heavily on the availability and cost of low-carbon hydrogen. Diesel or EV fuel oil backup generation remains one of the most common forms of emergency power generation for hospital, data centers, industrial facilities, telecommunication networks, and critical infrastructure. Its strengths include proven reliability, relatively low capital cost, rapid startup capability, and the ability to provide long-duration backup power through on-site fuel storage. Its main weaknesses are high carbon emissions, high pollutant emissions, fuel price volatility, increasing regulatory restrictions, and incompatibility with long-term decarbonization objectives. While diesel generators remain widely used for emergency applications, many organizations are exploring lower carbon alternatives such as batteries, renewable fuels, and hydrogen-based systems as sustainability requirements become more stringent. A high-level solar PV system design starts by defining the building's electricity demand and how the PV system is expected to contribute to it. This includes establishing annual electricity consumption, typically based on utility bills or hourly data, and identifying the target PV contribution, such as a percentage offset of annual demand or a specific self-consumption strategy. Peak electrical load is also a key design parameter as it determines whether the PV system is sized primarily to offset annual energy consumption or whether it can meaningfully contribute to peak demand reduction, depending on the natural overlap between solar generation and the site's load profile. Operational patterns matter as well, since daytime load alignment increases self-consumption and project value. At this stage, it is also necessary to understand the reliance on the grid for electricity imports as well as contributions from any other on-site generation such as CHP or wind. PV integration is also influenced by export limits, backup requirements, and overall grid connection constraints. The next step is a solar resource assessment, which determines how much solar energy is available at the site. This is typically based on average global horizontal irradiance, GHI, which describes the total solar radiation received on a horizontal surface over a year. However, PV performance depends strongly on roof orientation, tilt, and shading. Roof planes are analyzed by azimuth, direction, tilt angle, and each surface is evaluated separately. Shading from nearby buildings, plant equipment, parapets, or trees is modeled because even partial shading can significantly reduce output. From this analysis, a yield estimate is developed, typically expressed in kilowatt-hour per kilowatt peak installed per year, which in Ireland often ranges roughly from 800 to 1,100 kilowatt-hour per kilowatt peak, depending on orientation and shading. Once the resource is understood, PV module selection is made based on efficiency, physical sites, degradation rate, temperature coefficient, cost, and compatibility with site constraints. Higher efficiency modules are preferred where roof space is limited, while standard efficiency modules may be used where space is abundant. Module type also influences system voltage, string design, and inverter selection. System losses are then accounted for to convert theoretical generation into realistic output. These losses include soiling losses from dust on panels, shading losses from partial obstruction, electrical mismatch losses between modules operating under different conditions, DC cable losses due to resistance in wiring, and inverter conversion losses when DC electricity is converted to AC. Additional minor losses may include degradation over time and temperature-related efficiency reductions, especially in summer conditions. The effective yield is then adjusted further based on orientation and tilt. Panels due facing south in Ireland typically achieve the highest output, while east or west facing systems produce slightly lower annual energy but better morning or evening generation profiles. Tilt also affects performance with optimal angles, typically around 30 to 40 degrees in Ireland, though flatter roofs using mounting systems will have reduced yield depending on design. These adjustments are combined with the loss factors to produce a final specific yield figure for each roof plane. Finally, the number of PV panels is determined by dividing the useful roof area allocated to PV for each orientation by the area of a single module. The total system capacity is then calculated by multiplying the number of installed panels by the rated peak power of each module. The expected energy yield is subsequently estimated by applying the effective yield, accounting for panel orientation and tilt angle to the installed peak capacity, and then summing the contributions from each roof plane with different orientations and inclinations. Determining total inverter capacity comes after the DC side of the PV system has been broadly sized, and it is driven by both installed PV array sites and the expected operating conditions. Inverter capacity is expressed in kilowatt AC and is usually selected so that the DC to AC ratio, often called inverter loading ratio, is within a practical range, commonly around 1.1 to 1.3 for many commercial systems. This means, for example, a 1000 kilowatt peak PV array might be paired with 800 or 900 kilowatts of inverter capacity. The goal is to balance cost, efficiency, and clipping losses. Undersizing inverters reduces capital cost, but can cause some energy clipping at peak irradiance, while oversizing reduces clipping but increases equipment cost and may reduce utilization efficiency. Panel string design involves configuring how individual PV modules are electrically connected in series and in parallel to match the operating voltage window of the inverter. Each inverter has a defined MPPT, maximum power point tracking voltage range, and maximum DC input voltage, and the string design must ensure that the combined voltage of modules stays within these limits under all temperature conditions. Cold temperatures increase voltage and warm temperatures reduce it, so both extremes must be checked. A typical design process calculates the maximum string voltage at lowest expected site temperature to ensure it does not exceed the inverter limits, and the minimum operating voltage at high temperature to ensure that it stays within MPPT range. Once the number of modules per string is fixed, multiple strings are then connected in parallel to reach the desired system capacity while maintaining electrical balance across MPPT inputs. An MPPT channel is an independent electrical input within the inverter that continuously optimizes the operating voltage and current of a connected PV string or group of strings so that it extracts the maximum possible power under changing conditions such as irradiance, temperature, and shading. Each MPPT channel operates separately, meaning it can track a different best operating point for PV arrays connected to it. This is important when different parts of a PV system experience different conditions. For example, one roof facing east and another facing west, or one string being partially shaded while another one is fully exposed. Without separate MPPT channels, these mismatched conditions would reduce overall system performance because all connected panels would be forced to operate at the same electrical point. So when an inverter has two MPPT channels, it means it can independently optimize two separate PV inputs, improving efficiency and flexibility in system design, especially for installation with multiple roof orientation or varying shading conditions. The number of strings that can be connected in parallel to the same MPPT channel is determined by ensuring that the total current from all parallel strings does not exceed the maximum input current for the MPPT, which can be estimating by dividing the MPPT maximum current rating by the operating current of a single string under standard conditions. PV strings are typically grouped so that models with same orientation and similar shading conditions are connected to the same MPPT channel to ensure that consistent operating conditions and optimal energy yield. The number of PPT channels required for a group of strings with a given orientation is then determined by checking whether the total number of strings and their current exceed the available current capacity of a single PPT channel, taking into account manufacturer limits and design safety margins. If this limit is exceeded, additional MPPT channels are required to accommodate the strings while maintaining independent tracking for each orientation or operating condition. The number of inverters is then determined based on the total number of required MPPT channels and the number of MPPT channels available per inverter. This is also adjusted for practical considerations such as inverter sizing relative to total DC capacity, redundancy requirements, physical layout, and electrical distribution constraints. Non-Domestic Microgen Grant. The Non-Domestic Microgen Grant supports businesses including industrial, commercial, and agricultural operators in installing on-site solar PV systems to generate renewable electricity and reduce both energy costs and carbon emissions. It is designed specifically for small to medium scale behind-the-meter solar installations, typically up to 1,000 kilowatt peak, making it suitable for rooftops, car parks, and small ground-mounted systems. The grant helps offset the upfront capital cost of PV installation, making it more financially viable for organizations to invest in self-generation rather than relying solely on grid electricity. By producing electricity on site, businesses can reduce exposure to volatile energy prices and improve long-term operational cost stability while also supporting national decarbonization targets. Funding is provided on a per kilowatt peak basis, with total grant support potentially reaching up to approximately 162,000 euros, depending on system size and project characteristics. The exact level of support depends on the installed capacity and is structured to encourage scalable adoption of solar PV across different business types and building sizes. The scheme is particularly beneficial for sites with significant daytime electricity demand, such as manufacturing facilities, warehouses, farms, retail centers, and office buildings, where a high proportion of generated electricity can be consumed directly on site. This maximizes savings because on-site use of solar electricity typically offsets higher retail electricity prices rather than lower export tariffs. Thank you. If you have any questions or comments or suggestions regarding the content of this webinar, please contact the Audit Plus team at auditplus.euprojects@gmail.com. Thank you for your attention.